Hi everyone, my name is So from Korea University. Thank you for attending my talk. In this presentation, I will talk about our recent work on formal safety verification of smart contracts. This is co-work with Myung-won Lee, Jisoo Park, Hee-jo Lee, and Hak-juo. Smart contracts are digital contracts written in programming languages. In the slide, you can see the smart contract written in Solidity, the most popular language for writing Ethereum smart contracts. I will briefly introduce Solidity smart contracts using this example. First, there are global variables in the contract. There is a constructor function which can be executed only once when deploying smart contracts on the blockchain. There are two public functions which can be invoked by anyone. Users can send transactions by invoking these functions with some argument values. For example, suppose the X's balance is 15 and Y's balance is 0. Then, X can send a transaction for sending 5 tokens to Y by invoking transfer with the arguments in the slide. Recently, ensuring safety of smart contracts is emerging as a pressing security issue. There are two major reasons for this situation. First, smart contracts are immutable. That is, vulnerabilities in smart contracts can never be fixed once smart contracts are deployed on the blockchain. Second, more importantly, since smart contracts typically manipulate very sensitive data, even a single flaw in smart contracts can cause huge financial damage. Indeed, there have been a number of disasters due to security vulnerabilities in smart contracts. Therefore, developing techniques for ensuring safety of smart contracts is critically important. To mitigate this situation, in this work, we aim to develop a technique for automatically verifying safety of smart contracts. In particular, we focus on verifying the safety of arithmetic operations. Because smart contracts typically involve lots of arithmetic operations, and therefore, they are likely to be major sources of security vulnerabilities. For example, as you can see, arithmetic over-underflows account for 96% of CVs assigned to Ethereum smart contracts. To motivate our work better, I will show a real-world accident that happened in April 2018. As shown in the red box, an attacker exploited the overflow vulnerability in Smart Mesh token contract and succeeded to create huge amounts of tokens illegally. In the slide, you can see the vulnerable function simplified from the Smart Mesh token contract. As the function name indicates, the job of this function is to transfer money to someone via proxy. Specifically, the core functionality is implemented from line 10 to line 12. The statement at line 10 sends value tokens to a destination account. The statement at line 11 sends feed tokens to a proxy, where proxy is a transaction message sender that invoked this function. The statement at line 12 deducts money from the source account. There are also guard statements to transfer money safely. The first if statement aims to prevent underflows in token sender's balance. The second if statement aims to prevent overflows in token response balances. However, the function still has a loophole at line 3. Specifically, the first and the second guard statements can be easily bypassed with crafted arguments that makes fee plus value 0. For example, suppose all accounts have 0 balances, and the transaction sender invokes this function with the inputs in the slide. The inputs are represented in hexadecimal numbers. With these inputs, We can bypass the guard statements because all three conditions now evaluate to false. Consequently, the statements from line 10 to 12 are executed. Observe that a huge amount of illegal tokens are now created, even though all three accounts had zero balances initially. Unfortunately, existing approaches for analyzing safety of smart contracts are unsatisfactory. Specifically, bug finders may miss critical bugs. For example, among the 4 bug finders in the slide, only Osiris can detect this vulnerability. Now consider another vulnerable function. This function has a similar vulnerability to that of the previous example. Specifically, the statement line 3 aims to prevent the underflow line 4, but the sanity checking for the overflow by the multiplication is missing. Despite the similarity between the vulnerabilities, Osiris now fails. Existing verifiers such as Zeus or Ascent Checker are unsatisfactory too. For example, in this contract, all arithmetic operations are safe from over and underflows. In particular, it is noteworthy that the operations at line 14 and 21 are safe, although there are no direct safety checking statements in each function. To prove their safety, we need to discover some invariants hidden in the contract. However, existing verifiers cannot find such hidden information, resulting in false alarms. To summarize, all existing approaches for automatically analyzing smart contracts have critical limitations. The major weakness of bug-finding approaches is that they may miss critical vulnerabilities. This is because bug finders do not consider all the possible behaviors of the programs. On the other hand, existing verification approaches are imprecise. This is because they typically compromise precision to detect all vulnerabilities. Due to the inherent limitations of existing tools, users of these tools should put a lot of effort for manually investigating false negatives and false positives. In this work, we propose VeriSmart, exhaustive, precise, and fully automated smart contract safety verifier. VeriSmart is a new verifier that fundamentally overcomes the shortcomings of existing approaches. Specifically, since VeriSmart performs exhaustive verification, VeriSmart can find all vulnerabilities. In addition, VeriSmart is highly precise, meaning that it produces very few false positives. Now I highlight the experimental result. In the experiment with 4 bug finders on 60 smart contracts with CVE vulnerabilities, VeriSmart detected all known CVE vulnerabilities with a very low false positive rate. By contrast, existing verifiers missed lots of known critical vulnerabilities with a higher false positive rate. We also compared VeriSmart with 2 recently developed verifiers. On 25 smart contracts where Zeus produced false positives, VeriSmart produced false positives on 1 contract. By contrast, Ascent Checker showed less precise results, producing false positives on 12 contracts. Then, what is the key distinctive feature that makes VeriSmart outperform existing approaches? It is the ability to automatically infer and use transaction invariants hidden in smart contracts. Transaction invariant is a global property that holds under arbitrary interleaving of transactions. More specifically, it should be valid at the end of the constructor, and its validity should be preserved by executions of transactions. VeriSmart can perform much more precise verification by leveraging inferred invariants during the verification process. I will illustrate the concept of the transaction invariant with a concrete example. Let's consider a contract in the slide. Given this smart contract, VeriSmart infers the transaction invariant. The summation of balances is equal to total supply. We can check this invariant inductively. First, you can easily see that the invariant holds at the exit of the constructor, where all balances are initially zeros. Second, suppose the transaction invariant holds at the entry of the transfer function. Then, the transaction invariant holds at the exit of the function because the same amount of money is increased and decreased for each account. Finally, suppose the transaction invariant holds at the entry of the burn function. Then, the invariant is preserved at the exit of the burn because the balance and the total supply are decreased by the same amount. The concept of the transaction invariant can be depicted as shown in the slide. Having obtained the transaction invariance, now I will show you how transaction invariance can be used to precisely analyze smart contracts. Specifically, I will show you how to prove the underflow safety at line 21, where there is no direct corresponding guard statement in the function. To prove the underflow safety at line 21, we need to show that total supply is always greater than or equal to value. We proceed as follows. From the transaction invariant, we can derive that total supply is greater than or equal to the message sender's balance. Next, by combining this with the condition at line 19, we conclude the subtraction at line 21 is safe from underflow. The figure shows the overall architecture of VeriSmart. The algorithm iteratively searches for useful invariants until the contract is proven to be safe or the given time budget is exhausted. The generator aims to produce candidate invariants that are useful for proving the safety. The validator aims to prove the safety using candidate invariants given from the generator. For more technical details, please see our paper. Now, I will present experimental results in detail. To evaluate the effectiveness of VeriSmart, we compared it with 6 existing analyzers. Specifically, we considered 4 bug finders and 2 verifiers. For comparisons with bug finders, we used 60 smart contracts with CV vulnerabilities. For comparisons with verifiers, we used 25 smart contracts from the Jeff's paper. We compared these tools against the analysis results on arithmetic safety. Our benchmarks are publicly available. The table shows the evaluation results on the CV dataset. As you can see, VeriSmart outperforms existing bug finders in both recall and precision. Since VeriSmart is an analyzer that performs exhaustive verification, it successfully found all known CV vulnerabilities, achieving 100% recall. In contrast, bug finders missed a number of known CV vulnerabilities. VeriSmart also outperformed the bug finders in terms of precision, with an exception to Manticore, where it rarely raised alarms. Interestingly, using VeriSmart, we were able to find 6 incorrectly reported CV vulnerabilities. This was possible thanks to the capability of computing transaction invariants. On the incorrectly reported CV vulnerabilities, Osiris and Oyente produced false alarms. On 25 contracts where Zeus produced false positives, VeriSmart produced false positives on 1 contract, and the Ascent Tracker produced false positives on 12 contracts. In this experiment, we again observed the importance of leveraging transaction invariants. Specifically, without transaction invariants, VeriSmart produced false positives on 17 contracts. To show that VeriSmart can be used to verify other safety properties beyond the arithmetic safety, we conducted a case study on analyzing access control vulnerabilities. Specifically, we considered a scenario where security-sensitive variables can be updated by anyone without restrictions. For example, consider this code snippet. At line 6, we can see that the CEO address is the beneficiary of either. The problematic part is the line 2, where the beneficiary address can be taken by anyone. As a result, if an attacker becomes the beneficiary by transaction 1, then the attacker might illegally take some ethers when the benign user invokes the function buy drugs. To detect this kind of bugs, we specified safety properties by automatically inserting assertions. For the previous example, we automatically inserted the assertion as shown in the slide, meaning that CO address should be updated only by CO address. Then, VeriSmart fails to prove the assertion safety, and it can detect this bug. In this way, VeriSmart found all CV vulnerabilities related to this bug scenario. In addition, VeriSmart proved the essence of the bugs for 55 contracts out of 60 from the CV dataset. To summarize my talk, I presented VeriSmart, exhaustive, precise, and fully automated smart contract verifier. Each key feature is the capability of automatic inference and use of transaction invariants. With this feature, VeriSmart overcomes the inherent limitations of existing analyzers. VeriSmart is publicly available. Thank you for listening.